And again, if you want to add a little bit to this, that would help you, that's fine, but these are the big things. Remember, if we're going to do correlation or the R value, it has to be a linear situation. That example from the homework was not linear, so we said that wasn't really the best to use the R value for. On top of that, they have to be quantitative variables too. You might note that it has to be two quantitative variables. We can't do this with categorical. Second thing, we talked about this a lot. The correlation or the R value tells me the strength and the direction. It tells me two things. And again, we're going to use R to represent that. So kind of in general, that's what correlation is, those three things. On the sheet the other day, we looked at some graphs. So some things to think about with graphs and correlation. These are just some examples. Notice when we had a correlation when R was equal to 0, it was really spread out. But the closer we got to 1, the tighter they got to one another, the closer they got to one another. This one here, this is still considered a strong correlation even though it's negative. Okay, so the positive and negative only tells me direction, it doesn't tell me anything about strength. So all the R values, they have to be between -1 and 1. I can never have an R value of like 4. Okay, it has to be between -1 and 1. We talked about the sign a lot. The closer we get to 1 or -1, the stronger the association is. The closer we get to 0, the weaker the association is. And you guys did pretty well in the graphs the other day. Just a reminder, and you don't have to put those values in. That's another example, but to find the correlation, we're going to take these steps. Go stat, over to calculate, and we're going to use the linear regression. That'll help us find our R value. You don't have to do it by hand anymore. That's kind of more the same with that. Here is one thing though. This is the very last page. Sometimes statisticians get in trouble with this because they find out two things have a correlation, and maybe it's a strong correlation, but that doesn't mean there's a causation there. For instance, if I looked at these two examples, if I looked at number of workouts and I looked at my bench press max. Okay, so I'm thinking about being in the weight room. I looked at the number of times I worked out, and I looked at my bench press max. And I found out this was the scatter plot I ended up with. And I said, okay, that's a pretty strong correlation. They're pretty tight together, which makes sense. The more you worked out, the stronger you probably got. So in this case, it looks like this caused this to go up. So I would say there is a causation here. And that happens sometimes. Sometimes what's going on the X affects what's happening on the Y. It causes that to be the result that we have. Well, then today we came to class. We filled out the survey. One of our friends filled out the survey. And we did person number 1 and person number 2. And some of you said you got a situation that was pretty close together. So there was a strong relationship there, a strong correlation. However, with person person number one's answers cause person number two's answers to match? No. All right, so sometimes, even though we get that strong correlation, it doesn't cause causation. It doesn't mean the X affected the Y. And like I said, that's sometimes where statisticians get in trouble, is they see, okay, well, these two things have a strong correlation. That means this must have caused that. And that may be misleading. That may not necessarily be the case. So just be careful. Correlation doesn't mean causation. And like I said, that's kind of the synopsis of those two sections, 2.3 and 2.4. Knowing how to find the correlation, knowing how to use the table for correlation, and then throwing in this small thing here of, okay, does that mean causation? If I do have that